Hello, my dear students. How are you? Welcome to another series of Noodle Chopsticks. So, welcome to the new episode of the series, and we have already spoken earlier. The name for the series comes with the fact that when you are facing a challenge, a problem, a numerical, a question, there are two ways to do that. One is this noodle way, which some might find it very fancy or fascinating. I don't know why. And another is a chopstick way. It's a straightforward method. You go from point A to point B, no complications, nothing. So noodle method is, from my perspective, it's very confusing. It is going to be lengthy, it is error prone and very difficult to grasp. I cannot understand, I cannot explain. So what's the whole point of it? But then still many teachers follow that, and I always think there are two reasons for that. That's just my theory, that maybe those teachers have learned it that way. They learned it a difficult way and they don't know there's another way out there. Or maybe they know and they want to portray the subject as a rocket science, because if they show it's a rocket science, then maybe you will think, wow, what if I had not approached this teacher? Then maybe I would have never learned it. I mean, with due respect to the teaching community, I don't know. Maybe this is one of the reasons. But let's stick to the chopsticks here. So my name is Bhavdeep Sethi, and I'm going to make sure that you fall in love with physics. And I've done that for many students, because I say do not ever memorize physics. Physics is all around you in the nature, and that's how it is supposed to be learned. It's supposed to be learned in a way which is a fun way. Now, what is the series today talking about? It's all about surface tension and energy. Now, this topic is coming from one of the classes I was taking last week, and I was teaching surface tension and surface energy to the students, and I was teaching in a way that I have always taught, and the way that mostly it is taught in all the classes. But some of the students, they were very curious and they started asking questions, what if, why, and all that. And I was really amazed by those questions. It's more like they're trying to go into the details in depth. They're not convinced by the traditional way of learning the surface tension and energy, and they really want to know what's actually going deep inside of it. And that this is how I came up with this topic for today. So to explain you in a way that you will actually understand the complete thing, what's actually going inside those molecules when we are talking about surface tension and energy. So it's a little in depth today. So be prepared for that. So first of all, what is surface tension? Surface tension is something you might have observed, like these insects, they can easily walk on the surface, as in the surface of the water is a thin membrane. It's like a rubber membrane out there. So that's what the surface tension is. And similarly, but before I go into the detail, obviously, when I explain all this, so again, there was another example here. If you look at this drop of water, it's taking that spherical shape, and you can see it looks like all those molecules are glued together, maybe. So that is surface tension. Now, before I explain you what is surface tension and why it is, you need some prerequisites. And as with all my videos, I'm not expecting anything. Like I'm saying, okay, I will teach you from the very basics. So very basics, let's start with what is a hydrogen bond. And you might have known this because you have taken your chemistry classes. So what is a water molecule? So water molecule is hydrogen here. So and then another hydrogen here, and then you have an oxygen molecule here. And we know that because of all that polarity, this one is a positively charged, this is positively charged, and this oxygen is a negative charge. So we know that. But then there is another water molecule out there. So maybe there is another oxygen here, oxygen, then Mickey Mouse kind of. I mean, I really, when I learned this, to me it looked like a Mickey Mouse. So whatever. So this is negative, this is positive, and this is positive. So this negative, they will have a bond together. And this is what keeps the water molecules together, and this is what it gives a liquid state. So that liquid state of water is because of these hydrogen bonds. Now there are other forces acting here. So, but those forces are actually very weak compared to these hydrogen bonds. So usually in the case of water molecules, these are the hydrogen bonds that give it a state. Otherwise, this would have been a gas, obviously, right? So when these molecule bondings break, it becomes a vapor. So till it's a glass of water. So those glass of water molecules actually are connected by hydrogen bonds. Now you should also know if they come closer, there is going to be a stronger connection, right? You know, charge one, charge two. When you bring them closer, the force between them increases, kind of like gravitational force. So that's another prerequisite that you should know. One is what is a hydrogen bond. Secondly, if the molecules come closer, the bonds will be stronger. It's going to be a more attractive force right here. Those are going to be used to understand what is surface tension and what is happening out there. Now, potential energy. I mean, obviously, you know potential energy, but let's really understand. Again, this is coming from the questions that my students were asking. Surface energy. I mean, everybody's talking about that soap film and all that, but still not getting it. So let's try to understand. Take the example of this pen. So if this pen I leave it, it goes down. So if I take this pen and Earth as a system has done a positive work on it. Would you agree? There is a force downwards and there is a motion downwards. There's a positive work that the system has done. But when the system does positive work, don't you think the potential energy reduces? Right. So when I'm comparing, so let's say this was point A. I'll write it with white color. I like that. I don't know why. So this is point A and the pen was here and to the point B. So if I'm comparing point A and point B, there is a natural tendency of pen coming down. There's a natural tendency of the system doing a positive work here. So when the system does the positive work, the potential energy reduces. So I can say compared to point A and point B, there is more potential energy here and there is a less potential energy here. So when the system does a positive work, the potential energy is reducing. But now think about the pen being thrown up. When the pen is thrown up, from the system perspective, what is happening here? From the system perspective, the system is applying a force downwards. I threw it up and then I'm out of the picture. The system is trying to bring it back. So system is applying a force downwards while the motion is upwards. So you can clearly see the system is doing a negative work. And when the negative work is done, you can clearly see the energy is increased. And this is how the potential energy being high low is all about. And so we can take more examples here. If you're interested, we can take more examples here. So let's talk about a proton and proton. So let's say there's a proton here. So let's say there's a proton and then there's another proton. Now let's say I glue this, I just fix it. You have to understand all these prerequisites to understand the in-depth of it. So let's say proton is fixed here and there's another proton and I'm just holding. As soon as I leave it, there's a tendency of it to move that way. So the force is applied that way by the system here and the proton moves in this direction. So when the proton moves there, there's a positive work being done on it. So when the positive work is being done on it, the potential energy denoted by letter U decreases. So can I say it had more energy here, now it has less energy there? This is one thing that you are going to use when you try to understand the surface energy. Another last prerequisite here is something about sphere. Spheres are like unique. I mean, think about sphere. If you are given a volume, let's say you're given atta, something, putti, something is given to you and you make spherical shape out of it. So don't you think there's going to be minimum exposed surface area? So let's say given a volume, you make cuboids, you make cylinders, prisms, pyramids, spheres, but spheres are going to be the least surface area. Now, since you are physics Olympiad students, I give you a challenge. Prove it mathematically using calculus. You can do that. It's easy. So prove that for a given volume, the surface area of a sphere is the least out of all the shapes out there. So that's one thing you have to understand. For a given volume, volume is fixed. For a given volume, out of all the shapes out there, cuboids, cubes, prisms, pyramids, cylinders, spheres will always have the least exposed surface area. So that's the last thing you have to know. So now coming to our main agenda about surface tension. So what is surface tension? Let's talk about bulk versus the surface of liquid. So bulk of liquid, as in you go deep inside the liquid, there's something happening with those molecules. But there's something different happening at the surface level. So let's try to understand. Let's make some container here. So let's say there's a container here, and you fill this container with molecules of water. So let's say there's one molecule here, there's one molecule here, and I'm just randomly making. I mean, obviously there are so many molecules here, but let's make some of them. Now, when I'm talking about bulk, I'm talking about bulk as in inside this, and when I'm talking about surface, the ones that are just swimming over there, they're having some swimming party over there. Now, think about bulk molecules. Now, bulk molecules, would you agree that there are forces, those hydrogen bonds I'm talking about? So, there is a very high chance because it's all filled with molecules all around. So, there's a bonding with the molecule here, bonding with the molecule here, bonding with the molecule here, bonding with the molecule here. And all these forces will eventually cancel out. So even though there are a lot of forces acting on that molecule, the net force is zero, right? Now talk about the surface molecule. So surface molecules, obviously, maybe this molecule is getting a force here, maybe it's getting a force here, it's getting a force here, but there's nothing on top of it. We are talking about cohesive forces. Cohesive forces, just if you don't know, so there are two types of forces we'll talk about. One is adhesive forces. Adhesive forces are between two different types of molecules. So like water molecule and glass, that's adhesive. Cohesive forces are between same type of molecules, so water and water molecule. So there is no cohesive force pulling this molecule up. So obviously there is a force downwards. And please start listening carefully here because this is the key to this. So talking about this molecule, this has a tendency to fall down because the forces are either downwards or this way, or maybe they're the ones here maybe canceling out. But the whole point is there are all kinds of forces in all directions here, but there's nothing on top. So they will have a force, net force downwards, and they want to go down with that. So let's go to the molecular level, what happens, because I tried to explain at the macroscopic level, but the curious students of NSEP batch, they are really curious. So they've started, okay, what is actually going on? So what is going on here is this. So maybe it became wider, but let's ignore that. What will happen to this molecule? It wants to go down. This wants to go down. This wants to go down. This wants to go down. But they can't go down forever because think about the two molecules out there. If they compress too much, wouldn't there be a compressive force telling them to go back? You can't just squeeze the water molecules together, even if there are hydrogen bonds pulling them together. But you can't be squeezing too much because if you squeeze too much, there's going to be a repulsive force now. So it's like a spring. So as they start going down, they can't go down any further. And what will now happen is they will go down a little, but a lot of these are going to be piled up here. Why are they piled up here? Because they started going down. See how the surface was not smooth. Now, as they start going down, there is a compressive force and they go down a little, and that's where they stop. And again, that's another property that's usually not covered in the books, that the surface of water is actually very smooth compared to inside. Inside, there is a lot of randomness there. There's a pattern of molecule here, 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 but the surface is surprisingly very smooth. And the reason for that is again, one more time, this is being pulled down, this is being pulled down, this is being pulled down, and they come down, and there is when the compressive force says, now enough of it, don't come down anymore. And these are piled up very close now because think about it, this one comes in between. So the distance between molecules is small. And this is where that concept that I was saying, when the distance reduces, the attractive force increases. So now there is a lot of attractive force between these two because the surface has the distance has reduced a lot. So if there's a lot of cohesive force here, they're holding together. I mean, it's like this was trying to sink, and this is a little childish, but think about this way. This was trying to fall down, and everybody else says, okay, let's hold our hands together, and together we will float. And this is exactly what is happening. So there is a very strong hydrogen bond. So there were hydrogen bonds here, and there are still hydrogen bonds going down, but sideways hydrogen bonding is so strong that this looks like a rubber membrane. Think about difference between solids and liquids. What is the difference? Difference is we always say in the case of solids, the bonding is so strong that they form a shape. And this is exactly similar to that what is happening here. Even though this is the water molecule structure, these have so strong bonding, and I'm repeating it a couple of times, they have so strong bonding that it behaves like a stretched rubber membrane. They are together. Now let's say there was an insect. Now, when the insect comes in and actually maybe puts the feet here, this might squeeze down a little, but because of the bonding, what will now happen is they will try to restore the shape back because it's more like elasticity that you studied earlier. This is what will happen now. So the strong bond here is going to make sure that it doesn't break. They have such a strong bonding. This is what is surface tension. Now, if I think about quantifying that, and again, we have done earlier also in physics, everything is quantified. So when I'm bringing in the concept of surface tension, I have to tell you how much it is, and this is how much it is. So let's say what we saw here was from the side, but what if I see from the top? I'm looking at the surface. So let's say this is the surface of the glass. I mean, I'm looking from the top, and there is water here. So this is water. Now let's draw an imaginary line. If there is an imaginary line, remember how the molecules were holding together. So this molecule right here is getting a force from molecules there, and a force from molecules here, the force from molecules here, force from molecules here, molecules here, molecules here. And what about the other directions? Those directions don't matter because that's all internal to this system of the line. We have done that. System, outside the system, inside the system. So these are the forces that it is experiencing. And this force per unit length is what we call the surface tension. So surface tension will be quantified as newtons per meter. So let's say it is 100 newtons per meter. What that means is this line, if this were 1 meter long, there will be 100 newtons of force. Now, if you think about pen here, and then you pull the pen from the surface, those molecules that attach here, they don't want to break the bonds with others. So they will try to bring the pen downwards. But now you have to understand, this is one thing that many students miss. If you're trying to lift this pen up, there are the molecules on this side and this side. There are molecules on this side being pulled down, but there are molecules on the other side also. So in the case of this pen, if you're trying to lift it up, so how much force? Force will be the surface tension times this length plus this length. So it will be 2 times of the length. So again, we will see how that comes into picture when we talk about surface energy. Now, surface energy, again, there's a way to show that there is a wire and you pull that, but some students were still not convinced. So what we covered in the class was this, that there's a wire here, there's a wire here, you pull it here, and this is but that is how you quantify. But what exactly is surface energy? So let's try to understand what is surface energy. Now remember how I told you, if this object is at a location and I leave it, system does positive work on this. So when the system does positive work and brings to a new position, the potential energy has reduced. So that means it has more energy at this point. Now that's the whole concept here. So let's say there is this beaker of water. Now there's this beaker of water. So there are some molecules here, some molecules here, some molecules here, some molecules here, some molecules here on the surface. Given a chance, they would try to go back because remember the net force was downwards. There's a force here, there's a force here, so there's a net force downwards. So when they come down, there is less potential energy. Had this molecule been given a chance, it would come down to this position, this new position. So can I say this new position has less potential energy and this has more potential energy? So that more potential energy, and remember, potential energy is all relative. I can say this potential energy is zero. I can say it is 100 joules. I can say it is negative 500 joules. It doesn't matter. All that matters is the change in potential energy. So if the change in potential energy downwards is negative, so it has higher potential energy here. That is what matters. Whether it is 2 joules or 100 joules or 2000 joules has no meaning. Potential energy number has no meaning. If you do not understand that concept, then you have to see my other videos of this point. It's all about the changes in potential energy. So what we are saying is the change in potential energy just now was negative, means there is some higher energy right now. And same concept happens here. So from here to here, the potential energy would have reduced. So what I'm claiming here is there is some high energy here. And compared to this one, a low energy here. So there is some higher energy here. We can put some number to that. And again, it is all relative, but we have all agreed to work in a way that I'll show you just now. But the point is there is a higher potential energy here. And the systems, all the systems, that's the law of the nature that it tries to reduce the minimum, the energy content. And how can it reduce the energy content? By exposing the least number of molecules on the surface. And how can it do that? By minimizing the area itself. And this is where the concept of the water drops taking a spherical shape comes into picture. Because if given a volume of water, water wants to minimize its energy. How can it do that? It can do that by minimizing the surface area exposed. And that is only possible if it's a spherical shape. As I said, you should prove that out. Had it been cuboidal shape, any other shape, it would have had more area. So what would now happen is the energy of this molecule plus this molecule plus this molecule plus this molecule, all these contribute to some energy, and that is actually a potential energy. And because it is about the molecules on the surface, we call it the surface energy. So again, one more time, because this was a little confusing concept, I will cover one more time. Because my whole agenda of this session is to clear the whole concept of surface energy. So talking about this surface here, so let's say there is a surface here, there's a surface here, and there is a molecule out here. Let's call this molecule A. This molecule A on the surface has a tendency to go down. And if it had come here, it would have reduced its energy, because remember, the system is doing positive work here. So it would have less energy here, more energy here. So that more energy of this plus more energy of this plus more energy of this, all these more energies, those energies added together is called the surface energy. And one very beautiful way to understand how much it is via the experiment given in any book. So what we do in this is we take a wire loop like this, and then we put a movable wire. So this is a movable wire which can move like this, and you make a soap film here. So this blue thing is a soap film. Now, so think about soap film as a piece of paper. So let's understand that also. So let's say this is my soap film. It is very thin. So to me, it looks like there's a surface here and there's a surface here. But is that it? No. If you look at my magnify that, this thickness here, it may sound very small, but it's not zero. So there are molecules on the surface, there are molecules on the surface, but there are molecules in between those surfaces. So there are not every molecule is exposed here. So think about atta from your kitchen. So you make a roll of atta, you make a ball of atta. So there are certain molecules on the surface. Now you start rolling it. As you make it thinner and thinner, more and more of them are exposed. So you can clearly see the thickness there because that atta is thick, but you visualize the same thing here. If you try to make this thinner, you're exposing more of them. Now, this soap film, there are some molecules here and some molecules here. So what is the tendency of this soap film? It says, I want to reduce my energy. How can it do that? By reducing the area itself. So what it will do is it will try to pull this forward. It will try to pull this forward, and think of it from another perspective. There's a molecule here this molecule is only getting force towards the left. There is no force towards the right because there is no soap molecule towards the right. So there is a force on this molecule towards the left. That's another way to visualize. So there's another molecule here experiencing a force, another molecule here experiencing the force, and all these forces will try to minimize the surface of it. So even though from the naked eye we cannot see, what is actually happening is when the wire comes here, the area is reduced, but since volume is constant here, the thickness is getting increased as in more and more molecules are going inside those surfaces, between those surfaces. But then if you want to really stretch this, you will have to apply a force here. And how much will that force be? Force will be how much force is applied here. You just apply the equal and opposite. Now again, going back to our pen example, there are molecules on this side here, this length, but the other side also. Think of it like this. So there are molecules in contact from forward and backward sides. So there is a net force of surface tension that was newtons per meter times the length, but this length and the other length, so that is 2 times of length. So this is the force you have to apply. But you apply the force and let's say you stretch it to a distance of x. How much work would you have done? You would have done work is equal to force, but force is S times 2L times the distance x. So this is surface tension times 2Lx. 2Lx is what? This x times length is the surface here, and then the surface on the other side, that is 2 times of length times this dimension. So that is this area. So this is this exposed area and the other exposed area. So can I say surface tension times the exposed area? So that is the amount of work you do, and that is the amount of surface energy. Now that's what is happening at the molecular level, and that's why you will see all these soap bubbles and water droplets. They are all taking spherical shape because the surface area out here is minimum. And if it was that easy, then you like and subscribe to this. And by the way, I'll take some questions also here from the chat. But before that, I would like to announce this, which I have been talking a lot about, because many students said, "Sir, maths base camp was awesome. Can you bring something similar for physics?" Yeah, this is a base camp for physics where we're going to cover the basics of trigonometry and vector algebra. So this is where you will start learning the basic tools of mathematics. So it's happening on upcoming Thursday and Friday, which is 6th and 7th of June from 4:30 to 5:45 p.m. And the price was 149, but again, we thought it's very a little higher because the purpose is to pull the students to fall in love with physics. So we said, okay, 29 rupees. Just apply the coupon NSCP1. You know, if you click on the link down, it should automatically do that, give you for 29. But if it doesn't do that, put NSCP1. So the purpose of these classes is only one, to make everybody fall in love with physics. So you should be getting an idea about how you should learn physics or how you should learn trigonometry. Memorization doesn't work. Okay, so this is the base camp. I encourage you to join. And again, NSCP course is also going on. If you want to join the third module, the link is down there. And I don't want to speak too much about it. The main purpose was to clear the fluid mechanics, surface tension and surface energy. And I keep talking about these medalists, and I'm proud of them. So yeah, so this is where I'll take some doubts here if there are any. Uh, then after integration of its area will, you try to do that. I mean, take a sphere and see how it relates to the volume. Uh, yes, Rudransh, if you're already part of an SAP course, you have already been enrolled into the base camp, so you don't have to enroll for that. When will it start? It will be on 6th and 7th of June, 4:30 to 5:45 p.m. So it's a 75 minutes class. Okay, so that's where we land then, and fall in love with physics, and I'll see you soon, students. Keep up the high Josh. High Josh and high energy are needed for any dream that